All right. So this is the actual calculation of the Pearson correlation. You can't draw a scatter plot for this data because you don't have the raw data. You don't have the actual data values. You have intermediate values, which is useful. It's a faster calculation. And it's also done because it helps reduce cheating, frankly. You are not to use Excel or SPSS or a statistical software program on your calculator, on your computer. You're not. You have to use hand calculations. You need to use either the formulas from our textbook or formulas that you've cleared with me before the exam. All right? So, we need to use the full 4-step hypothesis testing procedure. So step 1, we need our hypotheses. We need an alternate. We need a null. It's a one-tailed test. So the correlation is something a little bit different than the other ones. The other test statistics that we've looked at this semester involve looking at mean differences or differences between group means. Here we're looking for an association between two variables. So where the other hypotheses have involved mu, this is going to involve rho. The correlation has zeros in the null hypothesis, and we're expecting a positive correlation with a one-tailed correlation. That means that we are expecting that in the alternate or the research hypothesis, that rho is going to be bigger than 0 because that's a positive correlation. And then our null, you flip and you put the equals under. Step 2, we need to find our critical values. To do that, you have a one-tailed test, you need your alpha level, and you need your degrees of freedom. N minus 2. N is 7, minus 2 is 5. We have a one-tailed test expecting a positive value, so it's off to the right. We're going to find what this cutoff value is. We are going to use, because I am not going to calculate the t. You don't need to. You can get by with just calculating your r value. You don't need to go into the t. If we're going to stop at calculating an r, then we need to use table B6, critical values for the Pearson correlation, right? If we were to calculate a t, then we would use the t distribution, but we're not. Doesn't make sense to me to do more work that isn't necessary. We're going to have a one-tailed test with an alpha of 0.05. So level of significance for a one-tailed test, so we're going to look up in this blue area. I just said 0.05. Okay, so we're going to look here in this column, this leftmost column of critical values. The very far left is our degrees of freedom, and we had 5 degrees of freedom. So our critical value is 0.669. And it's positive because we're expecting a positive correlation. Anything out this direction, we are going to reject the null and accept the alternate. Anything over here, we're going to fail to reject the null and be done. There's no more association. There's no consistent relationship. Step 3, I'm going to move on to a different page. So that's all together. Eventually, it's down here. Eventually, we're going to calculate R. And R is going to have the sum of products in the numerator, and it's going to have sum of squares x multiplied by sum of squares y, and then take the square root of it. We need those pieces, though. We don't have these. We need to calculate them. So let's calculate sum of products. Based on the information we have, we need to use the computational formula. So the sum of x multiplied by y, subtract the sum of x multiplied by the sum of y divided by n. xy was 1,266. The sum of x was 165. The sum of y was 48. And n was 7. So 165 multiplied by 48 is 7,920 divided by 7. So that's 1,266 minus 1,131.429. I'm keeping 3 decimal places here. Probably should have on all my other questions pretty consistently because my critical value has 3 decimal places. Okay. So 1266 minus 1131.429 is 134.571. I'm going to put that eventually down here. I need to calculate my sum of squares x and my sum of squares y. So sum of squares x, this is pulling a formula from, chapter 4. Okay. It is the sum of x squared subtract the sum of x squared divided by n. Sum of x squared was 4,271. Subtract 165 squared divided by 7. 4,271 subtract 165 squared is 27,225 divided by 7. So 4,271 subtract 3,889.286. Is 381.714. So that's going to go here. And I need to do the same for y. Sum of squares y. So I will take the sum of y squared, subtract the sum of y, which is then squared divided by n. That was 392 subtract 48 squared divided by 7. 392 subtract 48 squared is 2,304 divided by 7. So 392 subtract 329.143. That's 62.857. All right. Keep in mind that your sum of squares x and your sum of squares y, they're always positive. They're the sum of the squared deviations, and if you have a positive deviation, you square it, it stays positive. You have a negative deviation score, you square it, a negative multiplied by a negative is a positive value. So your sum of squares are always positive. Whether or not your correlation is positive or negative is going to depend upon your sum of products. Your sum of products is in the numerator, and it determines whether or not your overall correlation, this value, is positive or negative. So we have 134.571, and on the denominator we have 381.714 multiplied by 62.857. I'm running off the screen there. Sorry about that. So I have 134.571 divided by 62.857 multiplied by 381.714. Don't forget, I still need to square root that, right? So divided by 23,993.396. So I have 134.571 divided by 154.898. Which is 0.869. Keep in mind that in a correlation, the correlation can go from -1 through 0 up to +1. Okay? It can't go beyond +1 or -1. What that means is when you're calculating your correlation, your denominator, the bottom, is always going to be larger than your numerator, the top. At most, they are going to be identical. That would give you a perfect correlation, either +1 or -1. But the numerator, the top, is never going to be more than the denominator. Just can't happen. Not if you're calculating correlation. So I'm going to take that value that I just calculated, because I need to do step 4 of my hypothesis testing procedure. And the value I just calculated was 0.869. So I'm going to reject the null, accept the alternate. There is a statistically significant positive correlation between forest bathing and mental health. And then the next piece, though, and this one it isn't labeled as B, but this is, you can consider that's A and this is B. B, we need to calculate the coefficient of determination. That's R squared. We just calculated R. R was 0.869. So we take that, we square it, right? 0.869 multiplied by 0.869, and we get 0.76. This is a large effect size. The boundaries for R squared in the coefficient of determination are the same as the boundaries for R squared in a t-test. They're the same. We get there at a different way, but in essence, they are comparable.